Let T be a linear operator on R cube defined by T x y z equal to 3x minus 3y, x minus y, and last one entry is 2x plus y plus z. Then the rank and nullity of T are respectively four options associated. This problem is given to us, and we have to find rank nullity of this linear transformation. As T expression is given, or linear transformation is given by this structure 3x minus 3y comma x minus y 2x plus y plus z. This is the formula of linear transformation is given. If you focus on this one, 3x minus 3y, and this is x minus y, so you can say these are multiple of each other. So we can say that one is depending on other. So there are two independent entry in this triplet. So if we know one of them, then other we can easily known. So rank of this transformation is equal to 2, and by rank nullity theorem I can say nullity of this linear transformation is 1 because of two independent choice. This is very convenient method to find a rank of this linear transformation, and somehow this is easy one to discard options. So you can say option C is true, but sometimes it is not convenient to find a rank and nullity using this method. So what we can do in different case. So second method is find a matrix representation of any linear transformation, and then apply elementary row operation and try to find rank of the matrix. So first, to find a matrix representation of any linear transformation, we need a basis. So e1, e2, e3, these are standard order basis for R cube, and this is for domain basis. So we need to find image of each element and need to write linear combination of codomain basis. So it will be 3 1 2. I need to write basis in terms of linear combination of basis of codomain. So basis of codomain and domain is same, so this will be 3e1 plus e2 plus 2 times e3. Now need to write T e2. T e2 will be minus 3 minus 1, and last one is 1, and T of e3 is equal to 0 0 1. So we have three linear combination of this basis element. So I can write matrix representation with respect to this order basis. So if I write elements of linear combination or coefficient of linear combination along column wise, so 3 1 2, and second column will be minus 3 minus 1 1, and last column will be this. Now you can see we need to interchange r1 and r2 so that I can easily put 1 as a non-zero pivot element at a unit place. So it is equal to, so this is equivalent to 1 minus 1, 1 minus 1, 0, and this is 3 minus 3, 0, and third row is same as. So this is my equivalent matrix whenever I apply R1 to R1 to R2. Now put two elementary row operation together. This is R2. Now we are changing R2 as R2 minus 3 R1, and R3 as R3 minus 2 R1. Using these two elementary row operation, we will have 1 0 0 minus 1 0 0 minus 1 0 3, and the last column will be 0 0 1. So this is equivalent matrix of this one, and we can say that this is zero matrix, so I can delete this row, and we have only two non-zero rows. So rank is number of non-zero rows in a matrix representation. So rank of this linear transformation is 2, and using rank nullity theorem I can write nullity of this linear transformation is 1. And rank nullity theorem says rank plus nullity is equal to number of variable. Now this is second method, and the one is third method, which is sometimes convenient to find rank and nullity of any linear transformation. So because of nullity is the dimension of the null space, so in terms of nullity I can find rank also, means using nullity concept. So if any element x y z, suppose this is an element of linear transformation which is belonging to null space of T, so using the definition of null space I can write T of this element x y z is equal to 0, and by the structure of T I can write 3x minus 3y x comma x minus y equal comma 2x plus y plus z is equal to 0 vector. On comparing these two triplet, we have 3x minus 3y equal to 0, x minus y equal to 0, and last one is 2x plus y plus z equals to 0. Now try to set up matrix representation of this, or try to write coefficient matrix of this system. So coefficient matrix will be 3 minus 3 0 0, sorry, 1 minus 1 0, and the last row is 2 1 1. This is coincident, this matrix or coefficient matrix is same as matrix we obtained in second method. So after applying elementary row operation, the equivalent matrix will be 1 0 0 minus 1 0 3, and last one will be 0 0 1. So you can say that this is a free variable. So number of free variable is a nullity of this. So nullity of this transformation is 1, and using rank nullity theorem we can easily tell about rank. So if many times we have to ask a question, what is the linearly independent vector of the null space? And linearly independent vector in null space means indirectly he is asking or she is asking the basis element, because of basis elements are linearly independent. As and x3 is a free variable, so using this r2 sorry r3 I can write 3x2 plus x3 equal to 0. Using this one x2 equal to minus 1 upon 3 x3, and using r1 means row first, I can write x1 minus x2 equal to 0. It means that x1 equal to x2. If x1 x2 x3 are constituent of any vector, so x1 x2 and x3 are constituent of any vector, so I can write x3 and x2 is minus 1 upon 3 x3, and the x1 is same as x2, so it will be minus 1 upon 3 x3. If there is any mistake you can easily understand and make a correction. So if I took x3 as a constant, so remaining vector will be minus 1 upon 3 minus 1 upon 3 and 1. So this vector is linearly independent vector, and this is constant. So linearly independent vector in basis is only one, means and this is the basis element of null space, so nullity of this linear transformation is 1. So there are many methods to find rank and nullity, but sometimes we need to predict which one method is convenient, try to solve answer in within second. So as you can see, in first method we can easily tell about rank and nullity of this transformation, and sometimes it is the convenient way.